Greetings to one and all. I am here to present my research entitled A Deep Convolutional Model for Heart Disease Prediction Based on ECG Data with Explainable AI. Myself, Sreeja M U. I am a postdoctoral fellow at the Department of Electronics, Cochin University of Science and Technology, under the guidance of Professor Dr. Supriya M H, Department of Electronics, BSAT. These are the contents of my presentation. We will begin with a brief introduction into what my research topic is, followed by a related work section, and the gaps are identified, which led to the proposal of the model, and the objectives of the work, followed by the proposed methodology and results and discussion, and we'll conclude with the concluding remarks and future scope. So, coming to what ischemic heart disease is, ischemic heart disease can be defined as heart problems that are caused by narrowed heart arteries. And why does this happen? Arteries are narrowed when there is less blood and oxygen that reaches to the heart. This can ultimately lead to heart attack. Heart disease prediction is crucial in realizing the notion of intelligent heart care, owing to the exploding number of heart diseases being reported on a daily basis. So this is a statistics that is reported by World Health Organization. We can see that ischemic heart disease is the most spiking result that has led to the highest amount of death in the year 2019 and 2000. So as I said earlier, heart disease prediction is crucial in realizing the notion of intelligent healthcare in its entirety. A heart disease prediction model can be a valuable tool in healthcare for several reasons, the prime one being early detection. Heart diseases such as coronary artery disease or heart failure can often be asymptomatic or exhibit subtle symptoms in the early stages. A prediction model can analyze various risk factors from any kind of data to pinpoint individuals who have higher chances of ending with heart disease. Now, why we have chosen ECG is that it is the most economical and easy to access data that one can get, that can give you an actual analysis on how heart, what is the state of the heart diseases in a person. And since we know that AI models are black box models, and in a area where accountability is crucial, explainability actually gives you an ability to gives the model an ability to understand and interpret the decisions made by a predicted model. In healthcare, it is crucial to build trust between the healthcare and providers and patients. When using a heart disease prediction model, explainability helps patients and providers understand the factors considered by the model and the reasons behind the predictions. Coming to the proposed model, by combining the predictive accuracy with explainability, healthcare providers can enhance healthcare and improve patient outcomes. So, the proposed model trains a deep convolutional model that aims at categorizing input ECG images into healthy and unhealthy cases, and we have considered four major classes from the dataset that we have collected. The model also further analyzes the significance of explainability with two popular algorithms, LIME and GradCam, which helps to analyze the model that we have trained. So the related works that we have reviewed span two major categories, where we look into the models works that we have that were reported in heart disease prediction using deep learning models, and another set where explainable models for ECG based heart disease prediction is reported. So from the detailed literature review, the gaps identified are a large number of heart abnormality detection models are proposed in the recent research works. However, we could see that supervised models are not yet addressed, which are actually found to produce better results than the unsupervised counterparts. And similarly, models that address the most significant groups of heart diseases in the form of ECG image signals are not currently addressed. Actually, ECG is the most economical form of input data for heart disease prediction. And another crucial concern is that although explainability is crucial in domain like heart care, local explainability models like Lyme and SHAP have been explored, but image-specific models like GradCam have not yet been explored. So our main objective is to design and develop a deep CNN model for ECG-based IHD prediction with explainable AI. Moving on to the proposed framework, so this is a the this figure shows the major phases of the proposed model. The model actually aims at classifying ECG signals into four major classes, as I've mentioned earlier. And since ECGs can be visualized as image data, convolutional neural networks have been adopted for the same. The major phases shall be described now. It begins with data collection and pre-processing. The data for training is collected from the customized collection of physionets, MIT, BIH, arrhythmia dataset in the form of images. The images are initially resized in the dimension of 100 by 100 and normalized by dividing it with 255, the highest value possible. Now, moving on to the model design, another figure also provides the detailed architecture of the CNN. CNN architecture consists of two sets of convolution layers with 30 units each and 30 and 15 units respectively, each having a size of 3 by 3 filters. These layers are then followed by a batch normalization layer and a max pooling layer. We'll see the importance of batch normalization layers in the ablation studies in the result section. The purpose of the model, as I said, is to classify the input signal into four classes. Hence, the output final layer, you can see that the dense layer is of size 4. Output is of size 4. And moving on to the testing part, we have divided the data set into train and test sets, and we have divided it in the ratio of 60 is to 20 is to 20. And we have used 60% for training, 20 for validation, and 20 for testing. And the testing has been performed in the unseen 20% of the data. And for the loss function used for CNN is categorical cross entropy, and uh, the last one and the regularization methods that we have adopted is dropout and early stopping methods. And for optimization, we have used Adam Optimizer with an initial learning rate of 0.001. Now, coming to explainability, we have proposed Lime. We have analyzed Lime and GradCam, and we have found that GradCam have shown better results. The major steps in GradCam calculation are the gradient calculation. The gradients of the member class corresponding to the activations of the final convolution layer are computed. These gradients represent the importance of each feature map in the final prediction. Now, global average pooling is done. The gradients are spatially pooled by taking their average, and the heat maps are generated and visualized. The heat map is overlaid onto the input image to highlight the region that actually contributed towards the prediction. So, this will give you an idea on how our insights can be gained regarding how the decisions are made in the CNN, and we can identify the visual cues that influenced the predictions. Moving on to evaluation. Evaluation of the proposed model has been performed based on the popular evaluation metrics like precision recall, F1 score, confusion metrics, and accuracy. The datasets that we have used is Physionet's MITPIH arrhythmia dataset, a customized form of the same dataset. And we have also performed the evaluation for ablation study and as well as quantitative evaluation. So this is just the training plots that we have acquired for accuracy during the training part, the accuracy plots and loss plots for the train and validation sets. You can see that we have got a very perfect model without much overfitting, and the validation and train accuracy and loss plots actually seem to overlap. And the ablation study results, we have compared our actual model with baseline models. Like we have tried to remove each component and found reported the results. We have started off with a single CNN model, then we tried to change it to dual convolution model, and then we have incorporated batch normalization, which is when we got the best result. The best results are indicated in bold, and we have got an accuracy of 0.985, precision of 0.982, recall of 0.982, F1 score of 0.981, and the ROCAUC curve of region 1. So this itself shows that shows the importance of the second convolution layer as well as the importance of batch normalization, which is why we have got these elevated results. Confusion metrics also show amazing results. Only for a particular class Q, we have got a slight confusion for the model. Otherwise, the model the results achieved are amazing. And for the AUC ROC curve also, we have got a high result. This is the visualization map based on GradCam. Visualization, we have tried to visualize the results from each of the convolution layer and after the max pool layer, and we have overlapped this heat map generated onto the actual image and found out which part actually contributed to the particular class that it has predicted. We have taken samples from both true positive and false positive, and we have recorded the results. So coming to the conclusion, we have actually implemented an intelligent explainable heart disease prediction model based on a deep convolutional neural network, and we have also used line and gradcam activation maps for visualizing or for identifying what features of ECG actually contributed to the predictions. And we have achieved a higher accuracy, precision recall, and reference score of the particular values that we have reported. And future scope is to incorporate RNNs. We know that ECGs are actually time series data. So if we could try to incorporate recurrent neural networks or transformers, vision transformers, or echo state networks, it might have shown better results. Right now, the echo state network and chaos theory have been applied onto patient medical records, but we have plans on incorporating it onto our convolutional ECG data. ECG data on convolutional networks. So the research work is funded under the Chief Minister's Navakela Postdoctoral Fellowship for the project Smart System for Ischemic Heart Disease Prediction through Explainable AI. These are some of the references that I've used. Thank you.